All right. So we left off. We had most of our code structure in place. We kind of knew where things were going to end up in the final ROM. Um, Next step, we're going to see where they end up in memory once we load them into the N64. And so we've got a few things to kind of touch on. So, number one, we used all of these DDs and we kind of forced this value, but we still have this fixed gap macro working for us. And so I'm going to delete these extra 32 lines of code. Until we actually put data into them, they don't need to take up any space, really. So they'll just kind of be out there. So they will have their right place, they will have their right size, and they're going to butt up against that. Same thing kind of going on here. Now, this was kind of an interesting thing. So we, in the introduction, we used the exception return instruction. And so if I type that right there, that will actually occur at the 800 once we get copied into RAM. Now, the other location that we needed was 180. And so we've already got this fixed gap thing here for 300, but we can take and do that for 180 and put in another ERET. So right there, we've reproduced our exception handler for. So I am going to leave these. This kind of gives us that gap that we were doing before. Pretty useful. Pretty useful. And because otherwise it all looks like the filler bytes, and we want to be able to read some stuff in there. So now the next thing we really need to do is get these things loaded into memory in the right place. So to do that, I'm going to, and I'm doing this all inside of the main ROM source file. Eventually, I'm going to move this out and make its own source file and so on. But for right now, this just keeps it really simple so that I can just develop. So we're going to create a macro, and we can look over here to see our syntax. Curly brace on the same line. I always have to remind myself of that. We're going to call this exception init. And there's our curly brace on the same line and our closing curly brace. So what we're going to do here is we're going to actually call DMA cart and RAM. So I'm just going to take this and this. Now, if we look at this macro, it takes a start and an end. Remember, I created those end labels, and so we'll get to use them. So that's really good. And then the destination. So that's pretty cool. That's going to work out pretty good for us. This is taken directly from Crom's code on or Peter Lemon. Peter Lemon N64. He wrote all of the code that inspired me, but in addition, he wrote all of the emulation tests out in his github.com/peterlemon/N64. And so he wrote this DMA cart and RAM that we are about to use. So I'm not as familiar with it, but it's pretty straightforward here. So, that being said, we have the start, the end, and the destination. So, our start is here. Our end is here. And our destination is there. Now, this doesn't quite do exactly what we want. It's kind of an odd thing here. Remember that we pushed our exception handler beyond that origin 1 million so that it was in the ROM space. So, wow, this stuff's tricky. All right, sorry, I'm thinking through this because here, and I'll show you where we're at here. So the cartridge domain is this 1 million address. In RAM, it's the 1 million. And just to point out that this million is really more millions, and this is the billions. Actually, that's about 2 billion, I believe. So, and here is that 8 million memory that we were talking about. It's really 2 billion. That here. Before I talk about this in such weird ways, let's plug it in and see what I'm talking about there. So 2 billion, 32-bit address space, and because this number is literally only 1 bit, the very first bit is high. I know that it's half of 4 billion, which is a 32-bit address range. So we're at the 2 billion plus or minus. But it has a much prettier 8,000 number there. So here's what I'm going to do. I want to see where this ends up. In the ROM, in the 1000 range, or the 1 million range, I'm going to just run it, see where that ends up. But you know what? I'm going to go ahead and duplicate this line here and just change these. Oops, and then this one is 320. There we go. Now, one of the problems that we have here is... Oh, actually, no, we're okay. So what I was going to say is that DMAs, you have to wait for the previous one to finish before you can submit a new one. So these two running back to back would have that risk of, oh, I did 2 of them and I'm in a really screwy state. But if we go back and look at this macro, the first thing that happens here, so it loads the PI base, which is the cartridge address, and oh, I'm sorry, the cartridge control, see the A460. If we come over here, here the peripheral interface registers. So that's where it's looking at. So it loads up that base register, the A460, and does a load word on the status register using PI base, and we get the load that into T0. Then we check the third bit. We AND it with a 3 and see if the DMA is still busy. And here's just a delay slot. So here, bit 3. Oh, I'm sorry. The status register is this one. And bit 1, 2, and 3 is the error bit. Oh, we AND it with 3, which gives us only the lower 2 bits. My mistake. So we're only checking to see if DMA is busy or I/O is busy. And if those are busy, then we just loop back and we keep looping until they are not busy, at which point we will set up the DMA here with those instructions. So this happens at the beginning, and so it will check the DMA status, make sure that it's ready to go, and then do the DMA, and then this one will also check the DMA status until it is complete or available, and then it will execute those as well. So those should be just fine. Now we actually do have to call this code here. Details. And again, I love the NOPs. They just make the code so clear, and we can remove them after the fact very easily. Their performance impact is minimal, so on and so forth. So that's our normal init. Then the exception init, which should just be these DMAs. And we're going to get into some more registers moves. But right now, I just want to see what we get. All right. So one of the other things, I forget if I've shown it, but I did set up an F6 compile. This is built into Notepad++, and I say OK, and there is my compile. So kind of handy when I just need like that syntax check kind of thing. So debug exceptions. We will see what happens. All right. So again, the first section is my init, and then here we have our next inits. There should be 2 of these. So T0, T0. So each one of these code blocks is going to load an exception handler. So that sounds good. And I am going to load a new disassembly window, 8, 1, 2, 3, 1, 2, 3, 4. All right. So just a reminder, this is header and PIF boot code. So this is, we want to overwrite this. And so that is very intentional. All right. So All right, so our DMA should be good to go. We're setting it up. And now we are looping again because the DMA is not ready yet. So again, MAME does a great job. This is one of those, it's one of those actions. It's so easy to emulate and just make every DMA transfer be instantaneous. But that's not accurate and can actually cause problems in some games. So they do the right thing and they emulate the actual time it would take to transfer this data. That being said, I don't need to step on every instruction. We're going to wait there. And so if we look in the background, I did see this flicker, but I am not seeing what I was really expecting there. So I'm going to kind of reserve judgment. I'm coming down here. This is that 300 range. And so while this is decoded into instructions, the values themselves are actually over here on the right. And we can see things like this is the 8 megabytes in RAM. It actually gets converted into this instruction just because of how that interpretation goes. So it's kind of interesting. But we should start seeing something after this 320. That is our goal with this next DMA. So and that's it. And so we did get some movement here, but is it what we were expecting? Ooh, it's not really. So I think we're just picking up some garbage here. Remember I said I wasn't real sure where our cartridge would come in. And so that's kind of what I'm going to look for here. Okay, here's where our cartridge is at. It's actually in the A range, so that's good to know. Now, the reason I recognized it and can confirm that that is the correct range is I know this identifier at the very beginning, the 80, 37, 12, 40. And just to show you right here. Oh, this one does not show those values. Those values are these. Maybe I've got them handy here. All right. You can. Let's go ahead and just trust me that that word is what most folks refer to as the endian indicator. Just because the sequence of those bytes, those 4 bytes, always exist in the first 4 positions of the ROM, but depending on the endianness of the ROM, sometimes they're mixed up, and sometimes they have to be reshuffled to work. I'm not going to get into that. That is the first 4 bytes of the cartridge. That is what that is. So Now that I've found that, so let's see. Oh. Okay, so again, this is the cartridge loaded in memory. And here we can see our e-return instruction is in there. And there is our other one at the 180 mark. Otherwise, this is the A55. This is our fill value. So everything's really the way it needs to be. Here's where our extra variables are at that we're trying to dodge. We get up to the 400s and on our A55 stops. So this is definitely our ROM, where it occurs in memory. The question is, how can we get the right address? We could hard code it to this, but as soon as we type enough instructions or have enough data, the origin value, which is what this is based on, so right there, once we put huge amounts of data or whatever, this origin value can get pushed out, and it'll be, maybe it's 1.5 megabytes, and that's where these things will actually occur. And I forget, there might be a compiler error when that happens, but so all right, so we're gonna, I feel really stumped. I'm sure it's achievable, but I'm not positive how. So we're going to go look at the BAS documentation, and we want to know more about the origin. And so okay. All right, I think so. It looks like origin is an actual supported value here. So that's kind of interesting. Huh. And okay, so here origin returns the current origin, base returns the current base, or PC returns the current program counter, which is origin plus base. Okay. You know what? I might have to come back to this. Um, yeah, for now, I am going to. So if we look back at our main, we see that it's the same address that we specified with the origin and such, but with an A in the upper nibble. The upper 4 bits of that value is an A. So if we do 0xa 1 2 3 1 2 3 4 and we AND that, for all of these, we'll find out if that's right. We need to exit out of our main debug session here. It couldn't write to the file. All right, and okay. Oh? Okay, that is not going anything like what I want. So when we did the second DMA the previous time, it did appear that the status portion of this code was working as expected. Oh. Okay. So I think what's going on is it's going the wrong direction. The DMA engine, the actual registers that we look at over here, we go to the 460 range. Peripheral interface. So we have the starting RD-RAM address, and then we have the cartridge address, and here we have the read length and the write length. So these two registers are the ones that determine what direction the DMA is going to go. And if we go back and look at the code, the write length, store DMA length to PI write length register. So C, we can double check it that way. C, right there. So this is the PI write length. So I think this is trying to DMA stuff back onto the cartridge. See, this is what happens when you copy and paste code. You don't pay as much attention to it as you should. So, okay. So this is actually a RAM to cart. And I'm going to copy this and call this one cart to RAM. And okay. All right, so okay, so at that point our DMA is working, or should be. 1, 2, 3, 4. All right, so it's doing the actual DMA transfer now while it spins, checking those status registers. In the background, on this tab, we may or may not see our memory change. Hopefully. And hopefully it's to the right values. So we do have a 1 in the T0 register, which we can see is what's being used here. And we can look back over here and see that that 1 is DMA is busy. So that's what we're waiting on. Huh. So the A460 is our PI registers, and so here, 37. So there's the C, A46008, Wow. This is really not working like I wanted. So that's the DRAM address. That's the PI card address. Oh, okay. So here's one thing about this. So up here we see that um, this address is essentially 0. Okay, which is confusing. Absolutely agree. Uh, but this is one of those things you don't usually have to think about, but it's kind of weird. Um, so in the schematic, I'm going to zoom in just a little bit. Uh, One of the things that gets overlooked is that the RCP, this big chip here on the right, has a memory manager inside of it. And so the CPU on the left, it's actually kind of dumb in the respect of the hardware mapping of memory and everything. And so it literally has pins, it has a bus that connect to the RCP that just says, give me this memory address, or write to this memory address for me. And that's okay, and that works. But then the RCP has this extra work it's got to do. It's got to figure stuff out. And one of the things that it does is it actually converts the memory map. And so by that, what I actually mean is if we look down here, these are it's a little strange, but these 3 connectors here are the memory, the actual RD RAM. Now, in the RCP's world, that memory starts mapping at address 0, and that is our NOP instruction. But when the main CPU wants to talk to that 0 address, it actually is looking at the 8000 address. So because the DMA requests, the actual DMA happens inside the RCP needs to know the the address that it knows for the DMA, which is the 0 address, which is what we've got here. And that's where that value comes from. And it's weird, and I get it. It's weird. All right. But so then this second value, what the heck is it? If we go to the documentation here, the second value should be the cart address. So 0 was perfect for the RAM address. That's great. The cart address, oh, it looked like MAME crashed out on us. That's fine, because it was not right. So the 0 was converted from this 8000. It dropped the upper bits, and that was perfect. That was correct and expected. Now, this exception handler part 1 label points down to here. And we're ANDing it. That's not what we want. We want to OR it. So if we look at the A in hex. Huh. These addresses do get confusing. All right, so the just to be clear, the macro here for the destination address is correct, and that's what actually makes the value 0. So when we look at the disassembly and it's loading the 0 address, that's expected. And so then it writes that out. And now this one looks like it's going to be a little bit better. So we're going to do this new disassembly A4601234. All right. So right now we can see that it's just this one pattern. I'm not sure what that's supposed to be. But now we're going to put the cart address out there. So that's not... T0. It's loaded with 0, written out. Starts with 1,000, adds zeros onto the 1,000. Oh, wow. The 1,000 value should be the start of ROM. And we want to be well above that. We want to be that 1 megabyte above the ROM. So we take the start and we trim off aligned cart physical ROM offset. That start address because we are saying this base no. Alright, so it's using the base address and coming back with a stack of zeros. Okay. Well, either one of these are coming back with a stack of zeros, but I think it's this one in is what is being compiled in. No, that's the one. That's not the origin one. That is a result of this calculation. It really ends up being just this value, which is the starting position of the cart. Okay. Okay. We're going to have to take a really different approach. For now, I'm going to cheat. No, that doesn't help it either. If we take this value, we'll put it in there. So that pushes the 1 into the third nibble. And how big is this? Okay, so it's not the origin that it's pulling. It is pulling this base, and that is it's truncating off that 8. Oops. Because that's this upper bit, and so it's getting masked off there. So see, and the thing is, I would go in and like rewrite this code, but it's really simple code, and I'm still going to be dealing with this other stuff that's going on with it. So it doesn't really change anything here. All right, so that being said, wow, this is the longest compile. All I did was move that baseline inside. Wow, okay. Alright. Assembled in 25 seconds. Okay, that is alarming. But I have an idea of why. It doesn't make it any better, but knowing why really does help. Oh, not as bad as I thought. Uh, it did bump the file out to 2 megabytes. Okay. I was concerned that it made it like gigabytes or something big, but um, there is, uh, and I've hit this before, uh, in certain cases, uh, like in macros or something like that, the bass assembler is really reading and processing like 1 byte at a time. And so sometimes it will take a really long time to generate something really simple because it's not doing it efficiently. It's not doing it in, 32 bits or, 4 byte or 8 byte chunks at a time. It's literally just 1 byte at a time, and it's executing a lot of code. And so sometimes that happens. Um, so, but I like a fast compile, and that just does not feel right to me. There we go. Less than 1/10 of a second. That feels right. Um, all right. We're coming up on an hour. I'm just going to be staring at this for a while. I promise to show you the solution and hopefully how I get there. Um, Thanks for watching.